Hi, in this video, we're going to be looking at how to sketch a graph using calculus. Now, these techniques that we're going to be learning here or using here are not the first technique you should think of. If it's a basic graph that's been transformed somehow, if it's x squared plus 5, take your parabola and shift it up 5. Don't use calculus to draw that graph. But if it's not a basic graph that's been transformed that you know how to graph, then here's some things to think about. And I say things to think about. This isn't a procedure. This isn't a list of steps that you need to follow every time. These are things to think about. The first one I like to think about is the domain. Now, for the domain, of course, if there's a denominator, that cannot equal 0. If there's a log, the argument cannot be, the argument must be greater than 0. If there's an even root, the radicand must be greater than or equal to 0. And if there's trig stuff, it has its own vertical asymptotes. So each of those vertical asymptotes can be an issue in trig stuff. So if you've got tangent, cotangent, secant, cosecant, all of those have domain issues. Come to think of it, so do the inverse trig things, arcsine and arccosine. Those have domain issues. So if you have any of those, take a look at those. Other things to think about, the y-intercept. It's really not very important in terms of the shape of the graph, but it's super easy to find, assuming x equals 0 is in the domain, and therefore you want to find it. The x-intercepts, those are only something you would look for if they're easy. The oddness or evenness of a function, most functions are neither, and therefore that's not helpful. But if you happen to notice this, it can save you some calculations. Because of the symmetry. Asymptotes, yep, we need to look for those, and there's 3 kinds of asymptotes. We have your vertical asymptotes, horizontal asymptotes, and oblique or slant asymptotes. And then finally, we have the derivatives, first and second derivatives. And all of that information that comes from those derivatives, that's what makes this calculus. And whether you're using the first derivative test, the second derivative test, finding the intervals of increase and decrease, or finding the intervals of concavity, all of those things are just kind of in this one topic for me. So let's try an example. Our example is we're going to try and sketch a graph f of x equals x e to the x. First thing I'm going to do is look at the domain. Well, there's no denominator, no logarithms, no roots of any kind, no trig stuff, no inverse trig stuff. The domain is all real numbers. That's nice. What's next? I'm going to look for the y-intercept. Okay, since that x equals 0 is in the domain, so we're going to find f of 0. That equals 0 e to the 0, which is just 0. So we have the point 0, 0. Now let's take a look at x-intercepts. To find x-intercepts, we're going to set the function equal to 0. 0 equals x e to the x. Using the 0 product property, that gives us 0 equals x, or e to the x equals 0. 0 equals x, we already knew that. There's our 0, 0. We already knew that one. E to the x equals 0. Well, e to the x never equals 0. If you took the natural log of both sides, you'd get x equals ln 0. And of course, 0 is not in the domain of natural log. So there's no new solutions there. There's just the one x-intercept. Next thing I'm going to look at is the first derivative. So that would be f prime of x. And because the original function is a product, we're going to use the product rule. The first times the derivative of the second plus the second times the derivative of the first. And so this is e to the x times x plus 1. If we set that equal to 0 to find the critical numbers, then we'll have 0 equals e to the x, times x plus 1. That gives us e to the x equals 0. Again, there's no solutions coming from there. Or x plus 1 equals 0, which gives us x equals negative 1. Now, if I want the critical point that goes with that, which I do want because I'm going to draw the graph, then we're going to plug that in. We'll find that f of negative 1 equals negative e to the negative 1, or negative 1 over e. All right, the next thing I'm going to do is find the second derivative, f double prime of x. Again, we've got a product here. Because it's a product, we're going to do the first times the derivative of the second plus the second times the derivative of the first. This gives us e to the x plus x e to the x plus e to the x, which is really e to the x times x plus 2. And so again, if we're going to set this equal to 0 because we want to find inflection points, then we would have e to the x equals 0, but that doesn't, or x plus 2 equals 0, which gives us x equals negative 2. And f of negative 2 is negative 2 e to the negative 2, or negative 2 over e squared. And so we have this point as well. We have negative 2 over e squared. This was the point negative 1 over e. With that, I'm going to start drawing the graph. I don't know that we have enough information to complete this graph, but we certainly have enough to get started. And we don't know what other information we need until we start. First thing, of course, is to label the scale. Label the axes. Always do that when you draw a graph. All right, 0, 0. That's our x-intercept and our y-intercept. Negative 1 over negative 1 over e. That's going to be negative 1 over e. That's somewhere around here. And negative 2 over e squared is a little bit higher. It's right up here. Now, some information I no longer need to find. So this first point here, this negative 1 over e, or this middle point here, we knew that that was a critical number, which means it could be a max, it could be a min. It must be a min because the points around it are higher. So this has to be a minimum. It has to be going up like this. This is an inflection point, so it needs to be turning at this inflection point. That looks like there's probably a horizontal asymptote over here. So let's take a look. Limit x approaches negative infinity of x e to the x. Let's see, that's going to be negative infinity times 0. That's indeterminate. We need to find a way to write this using L'Hopital's rule. So I'm going to put that as x over e to the negative x. That's negative infinity over e to the infinity. That's over infinity. That's infinity over infinity. That is L'Hopital's. So we get, by taking the derivative of the numerator and the denominator, again, we're not taking the derivative of the entire function. This is not the derivative of x e to the x. We get negative e to the negative x. And when we plug this in, we really have 1 over e to the infinity. That's 1 over infinity. That's 0. So this does indeed have a horizontal asymptote approaching that x-axis. This was the inflection point right there. Now for this side, let's see what this is doing. See if there's a horizontal asymptote here. Oh wait, there can't be a horizontal asymptote because then it would need another inflection point. So the only thing this can do is go straight up. If you're not sure though, if you hadn't noticed that, it would be okay to find this. And it doesn't take much work to go, oh, that's infinity times infinity. That's infinity, which matches what we just said. Those are all the points I'm going to find. That's our finished product. If you'd like to make sure that your graph looks really good, then I would recommend either checking it on a graphing calculator or using a website like Desmos or GeoGebra or even Google Graphing to make sure that this looks right. I have checked it. It looks good. That's it for now.